about to ask. So, Jim, you're normally based out of Sweden, right? But
I
you're in
am, yeah,
Greece right now. Is
yeah.
it
No, no, I said
okay?
I'm going there. I'm just going there for vacation, like, with the family.
Oh, okay. Oh,
Just,
sweet. Okay, okay, okay.
yeah,
So, where are you based out in Sweden, in that case?
Stockholm, yeah,
Okay, okay, all
yeah.
right.
I know
No, I'm
Ali from
just
time. I used to work with Ali here for years,
right, right,
so
right, right. No, no,
yeah,
I'm
no
supposed to
problem.
go to I forget which conference, but also I believe it's in Sweden in November. I think it is. So I'm gonna have to,
Ooh, give us a
yeah.
shoot, like just like knock us up, and we'll
Oh
show you.
heck yeah! I mean,
We'll show
yeah,
you.
it sucks that I have to go to Sweden. I mean, that's such a horrible thing to go do. Yeah, wonderful country,
There's
beautiful
Sweden and
everything.
there's
Yeah, yeah.
Stockholm. There's Sweden and there's Stockholm. Paris of the North, you know.
That's right. That's right. Sorry, I hanged out in Bostad, so
All right.
everybody from Stockholm was giving me grief. Like, no, 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 no. That's the wrong part.
That's if you're going for there's a tennis tournament there. It's very popular, and the kind of
Yes, yes, yeah, yeah. I wasn't going for the tennis tournament. It was a buddy of mine was getting married, right? So then they decided to have, and they decided to have it in Bostad, even though a sizable chunk of the family is actually based in Copenhagen, which makes it even more interesting when I heard the Dane versus Sweden like
oh
debate that
yeah,
was happening during the wedding.
very good. Do you know what they say in Denmark? They have signs. Keep Denmark tidy. Show a Swede to the ferry, but there's no ferry anymore. You get the train over.
Yes,
Uh,
exactly.
But that's
How about you, Fabio?
history as
Where
well.
are you based? Also in Sweden as well? Oh, is Fabio frozen?
Fabio's on
Well, I'm
his.
based
Oh,
in
there.
Sweden
Oh,
usually, but then yeah. Sorry, I was muted. Yeah, I'm based in Sweden usually, but then I travel quite around. So I've been in the States for the past couple of weeks, and then right now I'm in Italy, and yeah, I'm going back to Sweden
ah,
next week again.
cool.
Yeah.
All right, no, you're going to someplace civilized, so we're good now.
Awesome. And we are live on YouTube and LinkedIn, and we have folks
Excellent.
joining us from Zoom. So I think we are ready to get started with today's webinar.
Brilliant.
So I'll kick things off. Good morning, afternoon, evening to everyone, and welcome to today's webinar on Delta Lake for Feature Stores with Hopsworks. We're super excited to have you all joining us today, whether you're tuning in from Zoom, LinkedIn, or YouTube. We will be doing a deep dive into the evolving landscape of machine learning systems, specifically through the lens of managing historical feature data. Let me start by introducing our speakers for today. We have with us Jim Dowling, co-founder and CEO of Hopsworks, and Fabio Busso, software engineer at Hopsworks, alongside Denny Lee, senior staff developer advocate from Databricks. Today, we're at the cusp of a significant evolution in how we manage data for machine learning. The challenge of handling historical feature data efficiently and cost effectively is one of it's something that we grapple with. And Delta Lake Feature Stores is an innovative solution that not only promises low cost, high performance storage and querying capabilities, but also brings to the table seamless integration and support for feature data management. Our speakers today are going to explore the added support for Delta Lake with Hopsworks, alongside existing support with Apache Hudi within the Hopsworks Feature Store, discussing the trade-offs between different table formats and the unique strengths and benefits that Delta Lake enables, the building of Python native ML systems with Hopsworks. We encourage all of our attendees to be a part of today's conversation. Feel free to submit all of your questions as they come up during today's webinar in the chat. But we have dedicated time at the end to answer all of your questions. And with that, I will turn it over to today's speakers.
Perfect. Thank you very much, Carly. Always appreciate you getting us off and running and getting us under control. So I'm actually going to go ahead and make it relatively quick because this was really about Fabio and Jim here, guys. I'm super happy for them to talk about Hopswork and the importance of feature stores in the first place. These guys are the experts in this area. So love the fact that they're doing this integration with Delta Lake. I will get to pine and talk about my love of Python and the Rust community, which is where the integration is from. But let these gentlemen start first. I'll be around to answer questions online, and then we'll definitely have this quick discussion right after the main feature presentation. All right, and without further ado, let me go ahead and switch over to Jim.
Thanks a million, Danny. Thanks, Carly, as well. So I'm Jim. I'm going to give a brief presentation of Hopsworks and the feature store on Delta Lake, and then I'll hand over to Fabio, who'll give us a demo of the platform. So hopefully you can see my screen and everything's good. So the title of the talk here is Hopsworks and Delta Lake. And what we're interested in here is talking about Delta Lake as a table format for feature stores. And also we have our own file system, which is tiered storage over S3. I'll just talk about how that integrates with Delta Lake as well and some of the benefits of that. But I'm going to talk a bit about AI systems and the importance of not just Delta Lake, but the importance of data management. So there are many different types of AI systems out there, and you can kind of break them down on many different axes. Here I've broken them down on two specific axes. These axes are whether a system is real-time or whether it's batch, and also whether that system needs context to make a prediction or whether it doesn't. So context you can think of as being state, external state, or whether the request to make the prediction has all the state it needs. So if you think of ChatGPT, it's a real-time machine learning system. You send it a query, a prompt, and it gives you an answer. It doesn't need any external information to make that. The large language model itself takes the input prompt, it gives you a response. You can think of it as being a stateless real-time machine learning system, an interactive system. Now, there are many other real-time systems that are not stateless, that require external state. If we take credit card fraud, for example, a credit card transaction will only have the amount of money on it, the credit card number, the expiry date, maybe the location. You'll need to get a lot of external information about the recent usage of that card, about the bank that card belongs to, and where the transaction is taking place before you make a decision about credit card fraud. And typically a feature store is the platform that provides that external context and history that we use to enrich our input request to make a prediction, to have richer inputs that we can make better decisions with machine learning models. And TikTok's personalized recommender, same thing. It has a lot of information about your recent history in terms of searching and what you've liked and what you haven't liked. And even if you take a large language model like Bing GPT, if you search on Bing GPT, not everyone has access, but it does make external calls. So you can ask it about something that happened last week, and it will be able to give you an answer because it's using RAG to do that, so retrieval augmented generation. Now, there are also batch machine learning systems like Google Photos, which do tagging, and it only needs the image to put in. You don't need any external information, so no context required. It will tag the images. But something like Spotify's weekly song recommender needs to know about your history. So it's going to go to some external store, in this case, the feature store, to get all the history about you to make a better prediction about what songs you might like to listen to for the upcoming week. So these systems are real-time, we have batch, but there's also embedded systems, AI systems, and mostly they're kind of real-time systems. You can think of Tesla Autopilot, maybe something in an industrial setting, making predictions on a factory floor about products being of good enough quality or not. They're often embedded systems. They don't rely on external feature stores to get the work done, but these are the basic 4 different types of machine learning systems that we'll see out there today. What they all have in common is that they all need data, and all of them need to be trained on data. And typically AI systems will need mutable data and large volumes of it, and that means typically columnar data stores. So columnar data stores, as we know, are used to store data for analytics, to store large volumes of data, and any AI system that's generating value will have new data that keeps arriving over time. So whether it's batch, real-time, LLM, you'll have a certain amount of data available. You can create a static training data set from that data, and then you can train a model. And then maybe more data arrives over time, and you'll take another snapshot of your mutable columnar data to create another model. And then finally, when you want to make a prediction in a batch system, you might take a batch of new data that's arrived recently and use your model to make predictions on it. So this is basically the columnar requirements we have for storing large volumes of data for training, but also for the batch machine learning systems. Now, if we go straight in and look at the table formats that you can use to store these large volumes of mutable data. The key point here is that it's mutable. We don't, you can go to Hugging Face and store a data set there. It's append only, but it's not mutable. And if you're storing data for enterprises and you need to, be compliant with the EU's GDPR, the Californian Privacy Act, you need to be able to delete data. So the data needs to be mutable. So that's where table formats come in, like Delta Lake, Apache Hudi, and Apache Iceberg, the big three, let's call them competing formats in this space. And they all have their different merits. So if we take Delta Lake today, it has the best support for Python today. And that's the main reason that Hopsworks is integrating with Delta Lake. We've added support for it. Hopsworks originally supported Apache Hudi, which doesn't have a native Python reader, which is a problem when you want to build a machine learning platform that will give you access to the data that's in Delta Lake or in Hudi for both training and inference, where we nearly always have a Python environment. So when we're doing feature engineering, we may not always have a Python environment. We may have Spark or Flink or some other environment, but when we're training and doing inference, we want to get that data to a Python client typically. So we can see some of the different merits of the different platforms. And, I think Delta Lake out of the box has pretty good performance, the best of the existing table formats. Hudi can be tuned to be good, which is a bit of work, and there is an advantage of primary keys in Hudi. But in general, you can see that depending on the type of problem you're trying to solve, some of the table formats will be best suited for your particular needs. I think in particular for machine learning and for feature stores, we do care deeply about Python support. We do care, of course, about being able to query the data efficiently. So having things like Z ordering and liquid clustering is great, and we do care about performance. Primary keys is something that is very nice to have from a developer perspective. You can work around it to some extent in Delta Lake when you don't have it. Okay, let's move on. So that's what we need. We need this columnar data to store historical data for training and batch systems, but we also need real-time data. So if I'm doing a real-time AI system that we talked about earlier, or a large language model with retrieval augmented generation, we'll need mutable row-based data because we need to get that data at very low latency. So it's the same basic principle. Data will keep arriving over time, and we need to be able to retrieve data based for entities. When we're making a prediction for an entity, which could be a customer or some other entity, we'll need to retrieve pre-computed feature data for that entity at low latency. So we're going to have a prediction service, which will have a request. Not all of these real-time systems will be able to have enough input data to make a good prediction, so they'll go to this feature store to get the pre-computed feature data, the context, which will enrich our prediction and give us better decisions from our models. So this is a different store. It's row-based. It's not column-based, so we're not going to use, obviously, Delta Lake for this. There are many different databases available for this. I'll kind of skim over this briefly, but some of the most popular ones are our particular database that we built called RonDB, which is a fork of MySQL cluster. So we are an ex-MySQL company, and it has, you can see, is all green, which is generally good. But there are other ones used out there like Dynamo and Bigtable are used by some other feature stores, and Redis is used by a few as well. And we know Redis recently went from open source to a less open model, unfortunately. RonDB is still open source, just out of a point of note. Now, so when you have an AI system, obviously the real-time systems need this real-time data. Batch AI systems mightn't necessarily need AI real-time data, but an organization that's investing into managing their data for AI will generally consider that, hang on, I'd like to have a central platform that I can use to manage my data independent of the type of AI system I want to build. So if I want to build a batch AI system now, or if I want to build a real-time AI system or an LLM, I'd like to have one platform to manage my data. And that's the same principle that data warehouses do for analytics. We have a data warehouse and we plug in our analytics and we get our data from there. So that's the basic goal of feature stores, is that we have one platform that stores all your data for AI. And from there, you can support these different types of AI systems. So that means you have integration from your data where we compute features from all the available data sources, and we store that data for the real-time applications, but also the offline data for training, as well as for batch inference or batch predictions. Now, when you build an AI system on a feature store, typically there's a very natural decomposition of your applications into three main, what we call machine learning pipelines. Now, you may have more fine-grained pipelines in this, but generally they'll fall into these three classes. There's a very natural interface. The first interface is the feature pipeline, where you have your data coming from all these different sources and will compute features. So these features are reusable features. They can be reused in many models for both training and inference. So we're going to transform this raw data into features and labels if we don't have labels available, and we'll store them in the feature store. That pipeline can run its own schedule, its own cadence. It can be developed in the best technology that you need for that. The training pipeline, on the other hand, will take that data, the features and the labels, and it will train a model. And the model will get stored in the model registry somewhere. And then an inference pipeline will run again at its own cadence. If it's a batch application, it'll run on a schedule. If it's a real-time system, it'll be a networked accessible service. But it's basically going to make predictions with new input data, either that'll come from the data source here, or it'll come from an application that sends requests and combine it with the data, the pre-computed data from the feature store. But it'll take that data and combine it with and use it with the model to make predictions. And this is a modular architecture. And what's really beautiful about this architecture is that it's independent of the type of AI system you're building. So if you're building a batch AI system or a real-time AI system or an LLM, this architecture fits for all of them, which is really nice when you're building teams that want to build AI systems. You can easily delineate and say, okay, data engineers and maybe ML engineers will work on the feature pipeline, data scientists and training pipelines, ML engineers and inference pipelines. Now, just to show you that this works for large language models, which are very new, this is an example of, this is available on Hopsworks GitHub repo. It's open source. It's an LLM for talking to PDFs. So you put your PDFs in a Google Drive, and we fine-tune an LLM based on those PDFs by extracting some text from them, and you can query them with RAG. So it's actually using not just similarity search, but there's some function calling in there as well. But basically, your feature pipeline takes the PDFs, chunks them, stores them in the feature store. We can create instruction data sets for fine-tuning from that. And we also then index that in an AN index in Hopsworks Feature Store for similarity search. And you can also call the feature store using function calling with RAG. So this fits in basically to the same general architecture that I described. Now, Hopsworks Feature Store introduces two abstractions, main abstractions. One is tables of features we call feature groups. And this is where the Delta Lake data is stored. So when a feature pipeline creates features, it'll store that data in Delta Lake. And the feature view is the interface to models. So when I want to train a model, I'll take many features from different feature groups, put them together, and that will be the interface to my model. And I'll use the feature view to create consistent snapshot of training data from it. And when I'm doing prediction, I'll use the same feature view for that same model to create the snapshot of pre-computed feature data for making predictions with. And that ensures that we've got type safety between training and inference. We don't get skew between them. Okay, so and we've also got support for external feature groups as well, which is another part. So if you have maybe existing tables in BigQuery, Snowflake, or S3, Parquet files, you can just mount those instead of copying the data in. Now, what's interesting here is that, if we think about, Denny mentioned Python and Delta Lake earlier. Of course, Spark is very popular for feature pipelines. It's incredibly popular technology because it scales, and it has a nice Pythonic kind of way of writing programs. We have the data frame abstraction, and we can write code in Python. But many people still prefer pandas or polars. Again, Python-based frameworks. And some people may like real-time streaming frameworks like Flink or Beam. But basically, there's a wide variety of technologies used for feature pipelines. But when we go to training pipelines and inference pipelines, we end up in Python world. Vast majority of machine learning models today are trained in Python, and inference is done as well in Python. So those particular pipelines will need to access the data that's ultimately stored in Delta Lake. And we need to get the data from their Delta Lake to these clients. And that's something I'll talk about in a little bit. Okay, so how do we firstly get the data into the feature store? So this code is basically Python skeleton code, and it could be PySpark or Pandas or Polars. You have an abstraction called a data frame. Hopsworks was in fact the first open source feature store, and it was the first one that introduced the data frame API as an abstraction for feature stores. So prior to Hopsworks, there were domain specific languages for defining feature stores where you would define in this DSL how to compute some features, and the data would get pushed into the feature store. But we have an open platform, as we saw earlier. It's an open modular platform where you can plug in your own feature pipeline, training pipeline, inference pipeline, And the way then you can plug it in is by providing your compute. So here it's a Python program which will compute a data frame, this featureized data frame, and we'll insert it into this thing called a feature group. So the feature group is this mutable table of data that's basically I kind of have online or offline access to. If you want to store the data in Delta, you have to specify the time travel format as Delta. That's kind of old syntax. We would call it table format now, but this has been around for a few years. So we had the term time travel format at the time. But once you've created the feature group, you just insert data frames into it. So this can be run on a schedule, run every hour, every day, and the data will keep obviously accumulating or incrementally be updated in that feature group. Now, you might do feature engineering, of course, in your feature pipeline. And one of the interesting things about feature engineering, of course, is that you can, if you do it in Python as opposed to SQL, because a lot of feature stores argue about doing SQL for feature engineering. But what we can see these days is that there's a wider variety of frameworks being used to compute features. So here I have an example of computing and embedding in a feature pipeline, which has become very popular things to do with an embedding model. And here we're doing some windowed aggregations with some on some counting some events and some time series data that's arriving, and all these things are becoming, the set of tools and frameworks available in Python-based frameworks is massively increasing. And I think what we're seeing is definitely a trend towards using more and more Python for feature engineering. That one we saw maybe a couple of years ago when it was very popular to do things like windowed aggregations in SQL. But when you have to mix it with other types of features, maybe that are computed in embeddings or other types, it's much easier then to do this in a Python-based framework, whether it's Spark or Polars or Pandas. So the last thing that's hard to do here, so you might say, well, why do I need a feature store here? Well, if you want to write the data frames that you're creating here to both the columnist store and the row-oriented store, and to have it consistent between them, and if you also want to, in our case, we support an approximate nearest neighbor index, so basically a vector database in the feature store, and this is all done transparently for you. You as a developer don't need to worry about it. Insert your data and it'll get there. Now, if I want to read the data from Delta Lake for training, so I want to read into my Python client, my features and labels from the training and test sets. Then I'll typically fit my model and make predictions and evaluate the model. This is the kind of typical code you'll see. I want to read that data from tables, and I don't want to have future data leakage if I've got some time series data. The time series data would be events that keep happening over time, and maybe I want to know exactly how many times the person used their credit card in the last hour at this particular point in time. You might say, well, you can go and write the code for that, but the code is it's very challenging, particularly for data scientists. So typically what you would have is, if you have your labels in a table called, in this case, the orders table, and we'll have to do an as of left join with the other tables that have our features. This isn't available in Spark currently. There is support in DuckDB, but there's not in Snowflake. So depending on your database, this becomes a harder thing to do. So what we do is we provide a very simple DSL for this based on the feature view. You create your feature view and it creates these consistent snapshots of data for you. So that's where the feature store makes your life easier. How we actually support reading data from Delta Lake into these Python clients is we built a feature query service. And there's a reference there to, we have a paper upcoming at SIGMOD in June called the Hopsworks Feature Store for ML, and there's some really nice details on this and some experimental performance results where we show that it's extremely high performance. But what we're doing here primarily is we're taking the data in a columnar format, so it's Parquet files in Delta Lake or Hudi, and what we do is we read those as arrow data into the feature query service that performs these point-in-time as of left joins. And then we return the data to the Python client, whether it's pandas or polars, or as arrow data. So the data is never serialized or deserialized all the way from the Delta Lake or Hudi to the client. And the data is also not transformed from column-oriented format to row-oriented format. So if you have a JDBC or an ODBC server here providing the data to the Python client, that means you have to transform your data from column-oriented to row-oriented back to pandas, which is column-oriented. So the client will have to transpose the data again. And that all adds up to making it really slow to read your data. So this is something that we've built that we're really happy with. It also supports federated queries. So you could have tables in Snowflake or BigQuery as external feature groups, and they can be joined together with the feature groups stored in Hopsworks in Hudi or Delta Lake tables. The last part is inference of our three-part pipeline. So we've batch inference and online inference. So batch inference, you read up some data from your feature store, maybe the data that arrived yesterday or the latest values for particular users. You make a prediction, and then you want to monitor the performance. In online inference, you get a request in, you join that request, you get pre-computed features from that request using the request information, maybe on-demand features to compute, you merge them together, you make a prediction. But all of this needs to be monitored as well for drift. So you want to have monitoring of the input data features, but also the predictions. This is not really easy stuff to do. So Hopsworks has support for feature monitoring since version 3.7, where you can basically, when you've trained a model and you have a training data set for a model, you can basically say, well, I'd like to create a detection window. So the reference window for your features or predictions would be the training data, will come from the training data. A detection window would be the new data that arrives since training happened. And you'd like to then maybe compare the statistics or look for typically statistically significant deviations in feature values compared to training. And this is just showing some syntax for how to do that. You can create a sliding window, for example, that's updated once per week. And then you can say, well, I'm going to compare the last week's data, 80% of it, to look for drift. And there's some canned algorithms that you can use for doing drift detection there. Now, I'm going to finish up by talking a little bit about Delta Lake, how it writes to our platform. So we don't use S3 directly. So whether it's GCS or Azure Blob Storage or AWS S3, and Hopsworks also runs on-premise. We have a tiered storage API called HopsFS that we've developed over many years. It's basically, think of it as being a globally coherent cache over S3. And Delta commit protocol relies on the file system provide this commit atomicity. Basically, we want an atomic move to commit transactions that have been executed in Delta Lake. S3 doesn't support that. We don't have atomic rename in S3, but HopsFS does because it is a HDFS API. Now, what it gives you is, like I mentioned, NVMe storage over S3, which is very interesting in machine learning, particularly with large language models, because if, for example, you have, Llama 2, which is 260 gigabytes, and it's stored in S3, and you want to read it up, because you want to maybe, train a model, or you want to do some inference, or particularly in your debugging, you want to basically improve the performance of your iteration cycle. If you're reading from S3, it's going to take 1,000 seconds roughly to load Llama 2, and that's too slow. If you're using NVMe disks now, I have 13 gigabytes down here because you can buy 13 gigabytes NVMe disks today. Unfortunately, you can't on the cloud. There's a reference there to a nice paper from Thomas Neumann from TU Munich who asks why we don't have 13 gigabytes NVMe drives available in the cloud. The max you can get is 2 gigabytes. It's a very good question, but on-prem, they're available today. And in that case, you can load 260 gigabytes into memory in 20 seconds, which is quite incredible. HopsFS is, it's this, the way it works, or the way it's architected is that we have these data nodes which basically store this cache data from S3. You access the data via a name node, and that will give you obviously access control, but it's also implements a globally coherent cache. So when you request a file, it knows which data node that particular file, its cached values or blocks are located at. So you'll go to the correct node and you'll read it directly from the NVMe drive from there, if it's there in the cache. And then the metadata is stored in RonDB again, which is another horizontally scalable platform. So all of this is horizontally scalable. So with that, I'll hand over to Fabio. I've been talking for quite a bit. I'm going to stop sharing. And
yep.
There was a question in chat, but that's Carly. So off you go, Fabio. Sorry.
All right, thanks. Let me share my screen. Can you see it? Yes.
Yes.
All right,
yes, it looks great.
Yeah. So, okay. Thank you very much, Jim. So I want to give you a little bit of a demo on how we leverage Delta in Hopsworks for creating features, managing features, and also I will leverage Delta Rush to sell those features to Python clients outside the Spark world, right? So as Jim was explaining earlier, right, we adopt this, let's say, best practices of separating the what we call a feature pipeline, so the feature computation from the training pipeline, from the inference pipeline. So we have kind of 3 different kind of notebooks that I'm going to go through to kind of show a little bit the different use cases for Delta in Hopsworks. So the first part is how do we create features and how do we register them in Hopsworks. So I have a notebook running in a Spark environment. In this case, it's running on a database cluster essentially. So this notebook doesn't do anything extremely fancy. It just reads some data from the Unity catalog. So we assume that, let's say, you have some data available somewhere in your data warehouse, and you want to use that data to create these specific features essentially, right? So in this case, we have a very simple example using two different tables, like a profiles table and a transactions table, and we are going to create a bunch of features from different environments, right? So this is running as Spark. This is actually running as Python, but the underlying engine is Spark. So we basically create a bunch of features. As Jim was mentioning earlier, the way the Hopsworks Feature Store works is by using an open API based on data frames. So we are basically essentially creating all these features using either PySpark operations or pandas operations. We're basically creating everything all together into a final data frame, which we then treat that as a feature group essentially. So let me skip a little bit this one for a second. This is basically, we go through the feature engineering, we connect to the Hopsworks Feature Store that is running on the cloud as well, and we basically then create our first feature group. The first feature group is the transaction feature group. We basically give it a bunch of metadata that we need to set, the name, the version, the description. This is to make it findable and to make everything like searchable and so on. We set the primary keys. So Delta doesn't necessarily have a primary key concept directly in the library, but we leverage the primary key information to be able to do upserts later on. So when you basically keep adding data, what's going to happen every time you run this notebook and you do an insert operation, down here, what's actually going to do is going to trigger a merge operation, right, in Delta. And we use the metadata information that you have registered here. So in this case, the primary key to determine on which column we're going to merge the two data frames. So we kind of simulating the concept of primary keys at the API level. Not only we do it at the primary key level, we also do it at event time, right? So the basic idea behind it is that when you have historical data, let's say in this case you have transaction for a specific, you're indexing on a credit card number. Obviously, the same credit card number is going to make a bunch of different transactions. And so what you're actually doing in the historical data, if you want to either append new transaction or update existing transaction, you will always have two items you're going to be looking for: the credit card number and the date time. So which is what we call as event time. Again, the merge operation is going to be done by the library itself behind the scene, but yeah, it's leveraging the Delta merge operation. We want to say that this is going to be available online. We want to build a real-time use case where transactions get scored in real time. We integrate with Great Expectations, so you can basically, this is what I skipped earlier on. You can basically define expectation suites using the Great Expectation API and determine like how different columns can be should behave, and with which constraints they should respect. And we basically register that information as part of the metadata for that feature group. And what's going to happen is that the libraries, before triggering the write operation, they're going to enforce this expectation suite. If it passes, then the write continues and the commit is made in the data table. If it's not, then the data is discarded and you get a notification. And then we basically I support a bunch of different table formats. We say we wanna support Delta only the metadata that you're gonna register once, and then every time we run this pipeline, either in streaming or in a batch scenario, what's gonna happen is that we will need to call this insert method essentially, right? And here, the first time it's just gonna create a table, it's gonna evaluate the table, and as I said earlier, all the times after that is gonna trigger a merge operation, keeping the data unique across the primary key and event time. We can add additional metadata. So one thing that once you have registered this feature, it's going to show up in the UI. So you can actually see that in the UI itself. You can look at the data as well, how data looks like, all the metadata that you have available, where data is being used, validation reports and things like this. And everything it's actually indexable. So if you're looking for birthday, I think it's so you're looking, for instance, what kind of features they are, be able to discover features and be able to kind of figure out which features you want to be able to use in your machine learning system, essentially, right? So you have a bunch of different things that the library does it for you, like computing statistics, both terms of like descriptive, distribution, things like correlation between different features, see which features are actually maybe correlated with each other you want to discard. And everything in this case is stored on OpsFS and then underneath on S3. So this is one use case. We have exactly the same concept on the other feature group that we're using. So we're using this profile feature group. Same idea behind it, different items, different configuration, but the same concept happened in this scenario as well. Delta allows us to do a couple of interesting things. As we add new data and as we add new information, there are two functionalities actually, that are really kind of useful especially useful in a machine learning settings, right? The first one is to be able to go back in time, right? So oftentimes you build this large data sets over many months or years, and then you have trained models at different point in time. And you want to, for any reason, go back and say, okay, well, I trained a new model today. The new model is not performing as well as the model I trained like a month ago. So I want to be able to kind of look at how data was a month ago, right? And so the data might have changed. Not only you have added data, but you potentially could have updated existing data prior to, let's say, a month before that, essentially, right? So one of the really interesting capabilities that Delta provides is be able to do time travel, which is why the field is named time travel format. And basically, we expose that in the API itself, right? So we basically say, this is my profile feature group that I want to query. This is the I want to get, and I want to get them at this point in time, right? And so we're going to use the Delta commits to be able to kind of look back in time and see how data look like at that specific point in time. And you can apply it on a single feature group. You can apply it on multiple feature groups. You can apply them on feature views. So to be able to kind of rebuild the same training data set as was in the past, essentially. And that allows you to be very flexible in terms of like maybe debugging things or reproducing training data set and so on. The other interesting capabilities that Delta has, and like all these new table format have, that maybe like if you were to use standard CSV files or Parquet files, is the possibility of deleting things much easier, right? So you can basically issue a merge operation asking to delete the records that match your merge operation. And we expose that in the API as well through these commit delete records, where you provide the API like a data frame containing all the rows that you want to delete, and then Opsus goes and does a deletion, and then you can trigger a vacuum operation whenever you want, essentially. So these are two examples of like underlying, let's say, Delta APIs that we kind of expose through the higher level feature store API, essentially, that will be available. So that's what we call a feature pipeline. So we have created the features. This is running in a Spark environment. what we want to do on the other side is looking at the read operation. So right, one of the nice capabilities that Delta provides is the ability to choose between different execution engine, right? So you can work with Delta in Spark, but you can also work in Delta using the Python ecosystem and using the Rust ecosystem, right? So I'm going to switch over to a notebook that I'm running locally to look at, for instance, how we're going to use those features that we just created to train a specific model, right? So we always this is running as a pure Python kernel. We just import a bunch of library and we connect with the feature store. So the thing we do, as Jim was mentioning, one of the challenges where you're dealing with a lot of different features coming in at different frequencies is that you need to align them and build like a point-in-time correct join, essentially, right? So that's done in DuckDB, for instance, using the as-of join operator, or there are different strategies if you're running Spark that allow you to basically build out temporary tables and temporary tables and them out as a point-in-time join. Both of these cases, obviously you need to be careful about what things you're joining and how you join them together. So one of the aspects we do is, in terms of API, we want to raise the level of abstractions, and we want to be able to say, these are, ask the user, just tell me which features you need from which feature group, and then Hopsworks is going to leverage some of the data that it has available, like which one is the primary key, which one are the event time, to be able to kind of construct join operation using the existing metadata and ensuring consistency, right? So that's what we do here. We basically select the features, how to join them, and Hopsworks is going to take care of building out that join. We have something called a model-dependent transformations. This is more in a data science world when you have dealing with obviously numerical data and the models. You want to be able to encode the data before providing it. We separate them from the existing, let's say, the existing feature engineering part to allow for things like reusability of features and allow for have different models, maybe leveraging different subset of the data and subset of the features. So that's what we're doing here. We're basically creating some of the retrieving some of the existing transformation functions, and we register them together with the feature selected as part of our feature view object, right? As Jim was mentioning earlier, the feature view in Hopsworks is that entity that enforces consistency between what data science uses for training and what maybe MLE engineer uses for inference. They refer always to the same object, which is the feature view in Hopsworks, and they provide them with the necessary features and necessary information to either build a trained data set or retrieving a feature vector that's going to be needed for real-time inference. Now, here is where the interesting part happens. Here, what we actually happen is that we are going to create a trained data set, right? So we are asking Hopsworks to kind of leverage the Delta RS and the RFI protocol that Jim was mentioning earlier to be able to create that trained data set for us. In this case, it's going to go through the two data tables that we have created. It's going to do this point-in-time correct join, and it's going to also pre-split this trained data set into 4 different items. So you can see them up here in the top. You can see we're going to get back 4 different pandas data frames. So train, test for the features, and the labels for training and test data sets. And so this is basically, again, the way the labels are decided up here. When we create the feature view object, we basically say this is out of all the columns that my query has, my feature selection has up here. The fraud label is the one that I'm going to use for label, essentially, right? So here again, we're basically accessing the data tables transparently from the user, and we basically just provide the user with 4 nice pandas data frame then they can use those bound data frame to train, in this case, like a simple XGBoost model, and validate that model, decide, figure out which one are, how the model is performing, and we then register the model in the model registry, essentially. So this is the training pipeline, accessing the underlying data tables as a read operation from any Python environment. This case is running on my local laptop, but it could be running anywhere, like SageMaker or Kubernetes cluster, or any different environment there. And finally, the last part is the inference part, right? It's actually starts here. What happens when we want to serve the model? What actually happens is that we want to be able to select which feature view you need for this specific deployment. We're going to be loading up the model in the container, doing the predictions, and then every time a new request comes in, we go to the online feature store. So we don't go to the data tables anymore. In this case, we go to the in-memory RunDB database that we have as part of our feature store platform. And we basically retrieve the necessary features to be able to make predictions. So the context to be able to determine whether or not a specific transaction was fraudulent or not, right? So, we get information about the credit card number, and we get information, like we retrieve the features needed from the profiles and from existing transactions and existing activities that were done essentially earlier. And then yes, this gets exposed as a Python API that allows you to basically query that information and so on. So that's the end-to-end example using Hopsworks and Delta Lake. That's everything I had for today.
Wow, this is really interesting stuff. And actually, I can honestly say that you probably answered pretty much any and all my questions. Jim was giving me the heads up about that. So, and there's actually only about 3 minutes left anyways before we're going to shut off. So I guess the only question, and you've already covered it, by the way. So in some ways, I'm actually making you repeat yourself a little bit, but I'm just curious, from your perspective, the usage of, like, what were the things, or like both the pros and cons? So I don't mind you calling us out here, right? For utilizing the Delta Lake Python library, a la using the Rust context. I'm just curious.
Yeah, I mean, I can take, so if we take the cons first, just to get out of the way, I think primary key is nice to have. So, the enforcing unique row IDs, because when you're creating training data, if someone has a pipeline and they write some data in and they wrote in some duplicates and they didn't realize it, that it's hard to identify that problem later on. You can Great Expectations is not designed to do that, and that's something that we kind of miss. But the most important thing is basically just being able to have a Python client that can read directly from Delta Lake, and that you have to have that, because I think most analytical data and most data for training in machine learning is going to end up on table formats, and you need to have the first class Python support for reading from the table formats, And I think, Delta Lake is just a good bit ahead right now. I know PyIceberg has made some support, but even in PyIceberg, if you write to a PyIceberg table from a Python environment, it's not partitioned at the moment. It just got merged. It's like, it's not quite there yet. And they need to do a good bit of work to catch up, I think, there. And Hudi is still very Spark centric and JVM centric. So I think our main decision criteria is here. We have to be the best. We want to be the Python centric feature store. We are the Python centric feature store, so we need to have the best Python support for the offline data, which will be stored in Delta Lake and other table formats.
Perfect. No, makes complete sense. And Jim and I were joking about this before we started, like how even though I'm a Spark contributor and even one of the co-authors for Learning Spark second edition, which, by the way, just as a minor note, got released in Japan. Yes, the Japanese edition got released yesterday, which is apropos for timing. Yeah. Every time I say the JVM, I start shaking again, right? It's just like right, because I'm like, no. In the realm of machine learning, we're basically solidly on Python, and then I love the fact that we're using Rust, as the basis for just for no other reason, memory efficiency. I can go on for hours, so I won't say anything right now. Jim, you're more than welcome to. I'm gonna shut myself down. That's
no, actually, but Leon Bam had a question, and it can actually point out I forgot to mention one of the other negatives. So,
sure.
but he's pretty good at cleaning up, right? Doing so. A database management system, of course, doesn't just serve data and actually queries. It manages the data. So, we have to obviously we'll have, if you have small files, we'd like to merge them and so on. This question was to optimize and vacuum on Delta Lake. So currently in our current release, you do have to do it manually, but of course that's going to come into the product in the very near future.
Definitely. And right now, there are, just to add exactly to Leon's both question and also Jim's call out, a lot of the stuff right now, like the auto optimizing, auto vacuuming, yes, that is not something that's within Delta Lake yet. There are both issues and PRs open to it. So like I tell everybody, go ahead and chime in. And tell us which one you're prioritizing. A lot of the stuff that we end up doing, for example, the votes that we got back were around, which really has nothing to do with today's session, by the way. We're like, this is why we focused on it, was because of things like uniform and things like liquid clustering. That turned out to be a bigger push, so that's why we weren't working on that. We did work on identity columns, by the way. I keep forgetting which state we're in on that one right now too. So it's not like we're not trying to put other features in as well. It's just like, well, literally, that's what the community voted for. So we're like, okay, so we're going to go ahead and do that. So from that standpoint, Leon and anybody else, keep chiming in on both the Delta user Slack and also the Delta Lake GitHub to chime in so that we can prioritize accordingly. Okay.
Brilliant.
Perfect. Okay, well, I think that's it for time. Carly, is there anything else that we need to shout out before we end the day? I definitely want to thank both Fabio and Jim for this awesome session. And the video is going to be propped up on the YouTube and everything, so it'll be available for everybody to watch and rewatch. So anything else that I need or forgot to add, Carly?
Nope, that's it. Thanks so much, Jim and Fabio and Danny. This was a great conversation. Thank you.
Thanks a million. Thanks.
And thanks for the awesome guests as well.
Perfect. Right. Thanks very much, everybody. Really appreciate your time all.
Thank you.
Bye.
Thank you. Bye.